I apologize for being so rudely interrupted by the limits of a screencast, but nevertheless, we're closing in. We're around the corner to the home stretch here. I know it's tough to listen for a long time to these, so we'll keep moving here. So, Newton's first law of motion we tackled. Newton's second law of motion says, what if there is a net force? What if forces aren't balanced? Then what's going to happen to the object? Well, it's going to accelerate. And the equation is incredibly simple. The sum of my forces, this is kind of my Greek letter sigma, which means sum. The sum of my forces, which is a net force, equals mass times acceleration. That's where we get a kilogram meter per second squared, because it's a mass times an acceleration, a kilogram meter per second squared. That's where we get that. So we're going to call that a Newton. And so we can measure that. Okay. Now the force, just like acceleration, just like velocity, is a vector. So it is not only going to have a magnitude, it's going to have a direction as well. Force due to gravity is going to be downward. Okay. And your weight is because you have a mass that's being accelerated by gravity. Okay. So those are a couple factors to play a role. So how do we measure, how do we determine this whole concept of force? Well, if I apply a net force here, this object is going to accelerate. Okay? Now notice, if I do this, here's Newton's first law of motion again. The object in motion is going to remain in motion. So that's all fine and well. But let's, whoa, that's not what we want. Let's go back to this puppy. And if we look at the speed here, let's bring this back to, rewind it here. Bring it back down to 0. Okay. So now, if I press on this object, notice that as long as I press on, I did it again. As long as I press on that object, let's move me out of the way here so I'm not an issue. This object will accelerate. So if I grab it and push on it, notice that I have a net applied force here. My speed will continue to accelerate. Okay, as long as I have that net force, this object will accelerate, which is why once you're out in space, okay, you will be able to basically accelerate to exceedingly fast speeds as long as you continue to apply a net force. So again, there's going to be an inverse relationship here between mass and acceleration. Okay, if I have a greater mass, it's going to be tougher to accelerate it. Okay, if I have a bigger mass, my acceleration has to go down for the same force. Conversely, if I have a low mass, my acceleration will be a lot higher. It's a lot easier to accelerate a ping pong ball rather than a bowling ball, okay, given the same amount of force. And finally, that leads us to Newton's third law of motion. For every action force, there's an equal and opposite reaction force. And again, let's go to this trusty dusty website. If I apply a force on this object, notice that as long as I've got some friction, lots of friction here, as long as I've got some friction, this force, this box is going to give me an equal and opposite force back. So these are Newton's 3 laws of motion, and really we're going to pretty much cover these a little bit more detail once we get a little bit further. I just want to give you a quick overview. Here this person's pushing a finger on the wall's pushing back with an equal amount. So this is going to be our starting point when we are done with the test, and we'll kind of keep moseying on this path of knowledge. We'll see the in-class group tomorrow, and we'll kind of clean up some stuff and get you the test preview. The other group, you are going to be doing some of those simulations that the B cohort got the other day. So we will see you tomorrow. Have a good day, guys.